In the previous example, we talked about Hooke's law forces, which look like F equals minus kx, and about the fact that the potential energy due to a force like that is 1/2 kx squared. So simply put, we're taking the negative integral of the force to find the potential energy function, such that the slope of the potential energy function at any given point is equal to the force at that point. That relationship summarized is F sub x, the x component of the force, is minus du dx. Now we want to connect that picture, which we saw for Hooke's law, with linear force and parabolic potential energy. We want to connect that to a more recent topic for us, which is how charge works. We know that we have Coulomb's law, which states that the force between two charges is equal to k sub e times the first q times the second q divided by the distance between the charges squared. And remember that k sub e here is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now, we talked about electric field, which is the force per charge. So just dividing both sides by that second charge, little q, we see that F per q, which we define to be the electric field, is KEQ over r squared. And now what we're saying is I'd like to have a function. If I could say that the force is the negative slope of the potential energy function like we have here, then the force per charge must be the slope of the potential energy per charge, U per Q. And we have a name for this thing. The potential energy per charge is called the electric potential. It's a little bit tricky that it's called electric potential, but it's not potential energy. It's potential energy per charge. And it has units, which are called volts. A volt is a joule per coulomb. So the relationship here is that the electric field is equal to minus the spatial derivative of the electric potential, which we call V. Take a look at what that looks like for a point charge. I want the function whose negative derivative looks like KEQ over r squared. So we know our force is KEQ over r squared, which is also the same as k sub EQ r to the minus 2. If we integrate this, we're going to get negative r to the negative 1, but we want the negative integral. So the electric potential due to a point charge of magnitude q is KEQ r to the minus 1, or KEQ over r. Now we can use this function as a way to visualize the surface that we're talking about when we imagine a surface that describes the electric field. Let's take a look at how we do that. I think a little bit of three-dimensional visualization really helps us to picture this thing. We're talking about the Coulomb potential due to a point charge, which we said is that Coulomb constant k sub e times the magnitude of the charge divided by the distance from the charge. So what this means is if we have one charge located at 0, 0, we can imagine that the other charge, another charge, will behave as if it were sliding on a frictionless surface of this kind of shape. So a positive charge is going to slide downhill away from this charge at the center and be repelled. So what would this look like if we had a negative charge? Well, of course, we would just be using a negative q, meaning we'd have this kind of shape like a pit. So in this case, if we had a negative charge located at 0, 0, a positive test charge would behave as if it was falling in, sliding down on this frictionless surface. And that's how we use the metaphor of the potential surface to imagine what the test charge will do. We can make this plot a little bit more useful by adding contours. So if we have evenly spaced contours like this, and we look down on this target, each of these color differences is the same drop in voltage. So if I imagine that this light blue to darker blue is occurring at 1,000 volts, and the next one is occurring at 800 volts, and then the same voltage contour interval, we'd have 600 volts down here. So we can really use the spacing between those voltage contours to estimate what is the electric field strength in between those 2 points.